Good morning. Happy Tuesday, everyone. I'm just kind of getting set up and ready to go. So I want to work on the last couple examples from the proportion chapters. That's my goal today. If we can get through those two chapters, we might be done a little bit early. I can't see it taking us a full hour and a half to do that, but I want to finish that up today. So just let me, let's see, let's pop over here. And I'm just going to capture those questions for us. That failed miserably. All right. Any big plans for the weekend, guys? Get rid of that. We're getting pretty close to having a nice 4-day weekend, right? I think next week is Easter. Those of you in my lab, I started posting some stuff up for the lab exam as well. So if you're in my lab section, you can go kind of take a peek at that. I've posted up a practice lab exam to give you an idea of what that's going to look like. And then, yeah, I'll get some more instructions out via an announcement as we kind of get closer. We have a couple-week break, so I don't expect most of you are going to go out of your way to take a look at all the instructions and stuff. Doing the section 3 test, yes. So yeah, casual reminder that the section 3 test is due by what, the 31st, I think. So make sure to kind of work away at that section 3 test. Or sorry, that one is due by the 28th. Yes. So 28th. Yeah, don't put that on your calendar. Don't forget to do that, please. And then, yeah, if you get a chance, you can kind of start working away at some of the data collection assignment 3 as well. If you are working with proportions, then you'll be kind of following a very similar procedure to what I'm setting up and doing in this particular chapter. So I believe that I had asked you to take a little peek at example number 2 and see if you could start trying to set this one up. And that's what I want to go through today. So we're going to work through creating a confidence interval to do a test. And then we're also going to work through finding and interpreting a probability number too. And both of these, it doesn't really matter which way we go. Both of these ways should essentially give us the same final answer. The confidence interval creating a big width where we kind of expect to see the target population fall. And the probability value goes the opposite way. It kind of calculates the endpoints and then tells us the probability that we're outside of the confidence interval. So they're basically two sides of the same coin is how I like to think about them. So for example number 2, we're taking a simple random sample of 200 babies, hopefully giving them back to their parents after we're done. We found out that 96 were male. Of those 200 babies. So we would like to test the hypothesis that the proportion of males born is 50%. So before actually going and setting up and doing a hypothesis test, let's try to gather some information. We want to essentially sort this information out into the target and into the sample. So we have an idea of what numbers go where. So that's typically what I try to do first. Okay, so what numbers go along with the target? What numbers go along with the sample? Well, the target population proportion is 50%. So we can think about the target as basically the set of all males that are born, or maybe all babies born. And 50% are male. So we're going to take a birth of a male baby to be a success, let's say, although that is very weird to say. So we'll take the probability of success to be 50%. The probability of failure will also be 50%. So you can spin it whatever way you'd like. If you'd like a male birth to be a success, or if you'd like a female birth to be a success, I will agree with you either way. So with that said, we can now move into the sample, which contains 200 babies. And we knew that 96 of them were male. So if we're taking P over here to be male births, then we should do the same thing in the sample. So we're going to use the 96 over 200 to make an estimate of how often we're seeing a male baby birth. So let's see. Let's divide that out, and this should come out to be a nice number. So we get 48%. So inside of our sample, about 48% of those that were born were male. Okay, so now that we kind of have the information matched up with what we need, we can now try to set up the hypothesis that we're going to be testing and then check to see that it satisfies the conditions in order for us to utilize some of the formulas that we've seen. So here's the setup. So we want to test the hypothesis that the proportion of males born is 50%. So I'm just going to copy that down. Now, obviously, if we look at strictly just the numbers, we look at our sample of 200 and we got 48%. So, I mean, strictly speaking, the proportion of males that we found in the sample is not 50%. But as we collect data on this random occurrence, this random variable, it's possible that we're going to see variation. So is it that we're seeing 48% as a random variation? And this 48% is really close enough to 50% that we shouldn't be too concerned? Or is it that inside this sample, it actually is truthful that we're seeing less males being born? So this is what we're trying to test. We're trying to test to see, is this 48% just kind of random fluctuation, a random variation in my data collection, or is it actually showing me something significant? Is it showing me something important? So the setup looks like this. We would like to test the hypothesis. So the null hypothesis, H0, is going to be that the target proportion is equal to 50%. So there's no change to what I would normally expect to see in the target. Okay, so I'm setting up the null hypothesis essentially to represent no change, or the idea that, without significant data, I don't want to assume otherwise that the target population isn't 50%. And the alternative hypothesis, because we haven't really specified that we wanted to lower something or see an increase in something, what we're going to do is we're going to take the alternative just to be not equal to 50%. I mean, if you walked in here and you said, I want to test the hypothesis that P is less than 50% because we have this 48% happening, that's fine too. I mean, I wouldn't argue with you. In this case, though, because there's no keyword saying like increase or decrease, I'm just going to take a not equals to sign, and I'm going to be testing that it's just not equal to 50%. So what you'll kind of notice is that unless it explicitly says to test a hypothesis that something has decreased or increased, we don't usually use those symbols, and we kind of default to a not equal to symbol. So this is the null and the alternative hypothesis. We're going to check to see if the sample really is 50% birth to males, or if it's something different, if it's showing us something different. Let's go ahead and check our conditions. All right, we would like to check independence. We do have a simple random sample, so that's helpful. And the other thing we'd like to check for independence with regards to categorical data like this is we want to make sure that we have the less than 10% criterion satisfied. So if we go back up and we look at our sample size of 200, we would like to convince ourselves that 200 is likely 10% or less of all babies. And I would like to think that that's probably true in this world that we live in at the moment. So for independence, we're pretty golden here. We have a random sample that's told to us in the question, and we can probably glean that 200 babies is less than 10% of all babies, so that our 10% criterion is satisfied too. So independence, I'm pretty happy with. Let's check the sample size condition. And for categorical data like this, we're checking to see if we have at least 10 successes and 10 failures. So if we take a male birth to be a success, for example, we have seen 96 successes. I'm going to put it in quotations so you can agree or disagree whether or not that is a success. And we'll take our sample size, which is 200, and subtract 96, and that gives us 104 failures in quotations. But the key here is that we have at least 10 of each of these things. Okay, so I usually shorten that to like the 10-10 success failure criterion is satisfied. So that's what I'm writing here, 10, 10, and 10. We need at least 10 successes and at least 10 failures. And we have that for sure. So our sample size is going to be large enough. And along with the independence, we can now utilize the central limit theorem. And we know that we're going to have a roughly normal sampling distribution. And if you want to be super explicit about it, we actually know that that sampling distribution is going to have a measure of center that's p, and a measure of spread that's equal to the two estimates multiplied together divided by the sample size, and all that's under the square root. So our standard error is what we call it, is given by this particular formula. So this just basically allows us to utilize the typical confidence interval formula that we've seen in this chapter. So let's go ahead and work away at that. So that's kind of step one. Step one is the setup. checking your conditions. Now we can actually move into the second step, which is to create this confidence interval and test the hypothesis. Now, remember I said that a 98% confidence interval, as well as 95, they tend to come up often enough that we probably should know the Z cutoff numbers. I think we've done this one already. So I'm going to just flip back in the notes, and I think this one's like 1.9, no, 1. That's a 95. Did we do a 98? We did an 80. Maybe we didn't do a 98 yet. 90, 95. Cool. Okay, so we haven't done a 98 quite yet. So we'll actually have to go through the procedure of finding this cutoff number. Once we have it, I would say just add it to your list of common ones, because 98 comes up often enough that you should know this particular Z star number. So the idea here is that for a 98% confidence interval, all of this stuff here in the middle needs to be 98%. Which means all of the stuff inside of this tail over here must be 1%. And what we're going to do is we are going to ask the calculator to find this cutoff number. It's going to come out to be a negative number because we're going to use the standard normal distribution. So the measure of center here is going to be 0, and the measure of spread is going to be 1. And we're wondering what this cutoff number is, and we need to use this cutoff number for our 98% confidence interval. So what we're going to do is we're going to set up the inverse normal distribution on our calculator. We are going to give it an area that's equal to 1%, a standard deviation of 1, and a average or a mean of 0. Alrighty. I don't know where I can put this so that I'm not covering something up. Maybe like roughly in here should be okay. So let's bounce into the distributions. We are looking for the inverse normal. We have an area to the left of our cutoff value of 1%. We have a standard deviation of 1 and mean of 0. So 2.33, let's say, negative 2.33 is going to be our Z star number for a 98% confidence interval. So remember, 98% is inside the middle, which means there's 2% in either of these tails. And because of the symmetry, you divide that leftover 2% in half. So that's why our area is 1% and not 2%. So like I said, this number is going to come up probably often enough that you might just want to write it down with some of the other ones. So you should have a list of, I think we've done 80%, 90%, 95%, and now 98%. Those are the most common ones. You might also see a 99% pop up if you're doing some examples, but those handful of examples are probably good enough for what we need to do. So it's just nice to have those so you don't have to do this calculation every single time if you happen to have access to these numbers. Okay, so that's the Z star number we need. Our overall formula for a 95% confidence interval will look like this. We are going to take our point estimate and we are going to add and subtract Z star times the standard error number. And now we just start filling some stuff in. So we saw that our point estimate was 96 over 200. That was 48%. That's how many male babies we saw born in that sample population. Our Z star cutoff number is 2.33. And then we're going to estimate the standard deviation here too by using 48% as our estimate for P. That's going to give us 1 minus 48%. So that's going to be 52% for female babies. And then we had 200 babies that we looked at in that sample population. And so I'm just going to share the screen here so I can show you that calculation. I'm going to bounce out of this and just kind of start working away at the lower bound of this interval. All right, so I get a lower bound of about 39.77%, let's say. What did I do that for? Okay. And apparently I exited out of the calculator rather than just minimizing it. So I have to type it all in again. Oh man, what a rough day. What a rough morning. Okay. Bear with me here as I just re-input all of this data just with a plus sign instead of a subtraction sign. And we have an upper number of 56.23. And then we want to interpret this confidence interval and then use this interval to see whether or not we're going to basically accept the null hypothesis or not accept the null hypothesis. So we've created an interval. So we know roughly 95% of the time So 95% of the time, we do expect to see that target population proportion, not the estimate, the actual true proportion, land in between these two numbers. Now, since the true target population proportion is 50%, and 50% lies on this particular interval, we really don't have enough evidence to not accept the null hypothesis. That's going to be our final conclusion. So our interval starts at, let's say, it's pretty close to 40 and runs all the way up to about 56.23. And our true target population is somewhere inside here. It's like somewhere in here, right? So our true target population is about 50%. So since the true target population does land inside of this confidence interval, there's no reason to suspect that us seeing 48% in the sample is anything more than just random variation in our data collection. And so our overall conclusion based on the confidence interval is that we're not going to reject the null hypothesis. We don't usually say something like accept the null hypothesis because we don't really know with 100% certainty whether or not it's true, but we have substantial evidence, I think, based on this interval to suspect that it's probably true. So we're not going to reject it. We're going to basically assume that it's still true based on the confidence interval that we have. So that's the confidence interval approach to setting up and executing a hypothesis test. If you're happy with that, just shoot me a little thumbs up or a yes in the chat, and we can start working on what a probability hypothesis test might look like. So personally, I like using confidence intervals to do some stuff like this. It feels very straightforward. What we're going to be doing next is calculating the cutoff numbers. So we're essentially going to be using the data that we have to find cutoff values and then trying to figure out what are the odds that I'm seeing a cutoff value that's this far away from the center of our sampling distribution. And then we're kind of calculating that probability number. So I'll show you how to do that so we get a little bit more practice with this. Typically, only one or the other will be used. So typically, you only need to use one unless it's stated in the question. And more often than not, if you go to read literature, they're going to be using the probability number approach. So what did I say for number 2? So create CI and test hypothesis. This will be the p-value approach. So normally I would go ahead and I would set up my null and alternative hypotheses. I do all of the condition checks still, but we already did that at the very start of the question. So I'm not going to go through that again. We're basically just going to accept that these are the null and alternative hypotheses. These are going to be the hypotheses that we're testing with this probability approach. Okay, I'm not going to check the conditions because we've done that already. And so the main idea of the probability approach is we have a sampling distribution that has a center of 50% and the standard deviation that's given by that square root. We want to see roughly how far away 48% is from 58% on the sampling distribution. So let's calculate what the standard deviation should be, maybe to 4 or 5 decimal places. And then what we're going to do is we're going to utilize the normal CD function, I believe. So what am I trying to do here? I would like to get the calculator, there it is. And I'm just going to do a quick calculation of this square root. So I apologize if my calculator is in the way here. I will remove it in a moment. Okay, so let's take 0, 3, 5, 3. So yeah, let's take a few decimal places, like let's maybe take 4 decimal places just to try to help with the accuracy a little bit. Not that I think it's going to change the question too much. So 0, 3, 5, 3. So the more decimal places of accuracy you take in this, so I'm kind of rounding, but the more decimal places of accuracy you take here, the closer you're going to be to an actual computer generated kind of solution. So the closer you would get to a Microsoft Excel kind of given solution as well. Okay, so now we basically have enough information to draw the picture and execute what we need to on the calculator. So let's go ahead, let's draw what this is going to look like. So here's our sampling distribution with our center of 50%. And we had a number that seemed relatively close to the center, but just over here, right? So we had a p hat, or an estimate of about 48%. And what we're going to do is we're going to utilize the calculator to tell us how much area is over here. And then we're going to utilize that and kind of mirror it on the other side as well. And I'll explain why we're going to do that. But first, let's get this probability number. So we're kind of asking ourselves the question, what's the area in here? Or what's the probability that I see a number like 48% or lower? So the question is, what's the area in here? Or what is the odds? What are the chances we see 48% or lower? So we can do this with the normal CD function. Because we have the cutoff number, so we use the normal CD function, because I know the cutoff's going to be 48. We're going to take a lower to be something like minus 100, just something really, really big and negative. We will take the upper to be 0.48. And then we calculated the standard error. So we're going to use the standard error here of 0.0353. That's going to be our measure of spread for the sampling distribution. And then our measure of center for the sampling distribution is 0.5. It's going to be 50%. So let's go ahead, let's plug those values into the calculator and see what happens. Okay, so going into mode, down into the distributions, we're going to be using number 2, which is the normal CD. Let's take a really, negative 10 would probably work, but I always like to go a little bit extra. Upper is going to be 0.48. Okay, 0.0353 for our standard deviation. And then the center of this sampling distribution is 50%. Cool, so we're getting a probability number of like 28.55%. So already I know, because this p-value is pretty big, I don't really have to do too much more thinking about this problem. I know that the 48% that we're seeing is really just random variation. It's pretty close to the 50% marker. I think it was like 2855 or something like that. Yeah, so in other words, the probability of seeing something like 48% or lower is 28.55%. So there's a pretty good odds, like what 28 out of 100 times, like pretty much 30% of the time, we're going to be seeing something like 48% or lower. So it really isn't terribly surprising to see a measurement like this. Hopefully that makes sense. So in other words, the probability is telling us that this is really not an unusual kind of measurement to see. It's going to happen like almost 30% of the time. That's not unusual. Remember what I said? The industry standard is to look for a probability value that's close to 5%. As soon as this probability gets really small, then what we're seeing is we're seeing a data value that we're getting from the sample that's really, really unusual. So to get a p-value of around 30% means that the sample that we're taking, the measurement we get from the sample, really isn't strange. It's not unusual. So in other words, again, without even kind of finishing up this question, technically there would be another extra step that we would take just to kind of really double check that we're in happy territory, because the distribution is technically symmetric. Sometimes you also need to check in the other direction away from the middle as well. But because we get this probability number that's already huge, I don't really need to check the other side of the distribution. I already know, just based on this probability number, that there's lots of evidence already to not reject the null hypothesis, and that the 48% that we're seeing is really just random variation. For those of you that are curious, if you've been reading the textbook a little bit, sometimes what happens is you get a pretty small probability value, and you're like, I do need to sometimes check the symmetry of the distribution. So I think this is going to happen maybe in the next example. Let's see. Yeah, it's going to happen in the next example where we get a small enough probability number that we do have to check the other side, the other tail as well, and kind of factor that area in too. So let's work on example number 3 if you guys don't have any questions, but hopefully you see that this kind of lines up with what we saw with the confidence interval. So with the confidence interval, this p number of 50 was, pretty centered, right? It felt like it was kind of like right smack in the middle of this confidence interval. So the closer this target population is to the middle of the confidence interval, the higher our p number is going to be when we go to actually do the probability method. And in fact, I'll just write this as a little side note. For those of you that have been doing a little bit of midnight reading, technically we would multiply this probability number by 2 for symmetry. And what is that number? So it would be 0.2855 times 2. So an even larger probability. And this is due to the symmetry of the sampling distribution. And kind of what I'm arguing is we don't really need to do that in this particular case because the p-value is already so damn big that even if I multiply it by 2, I already know it's huge, and it's not going to affect the overall question. And we do this, again, it's kind of like just for curiosity, if you're curious, We do this to kind of check the following. So if I know that the measure of center is 50%, and I know that the sample I took was about 48%, and I know that this area is about 28%, we're also checking up here as well. We're kind of also checking to see what happens in this tail. We're going to also check 2% higher than the center. So if 48 is 2% lower, we're also going to check 2% higher. So this 57.1% essentially tells us the odds that we see something that's this far away in either direction from the middle. So this is a kind of a standard convention that we use in stats just to be extra careful. So in other words, if I go and collect 200 pieces of data, I could get 2% less than what I expect to see, which is what we saw in our written example. We got 48%. I could also go and collect 200 pieces of data and be 2% higher and still be the same number of standard deviations away from the middle. So it's very typical to read studies that will use a two-sided approach just to kind of be a little bit more careful about the probabilities that they're talking about. And that's technically what we should be doing here. But like I said, with a probability number that's really high anyway, you don't really have to consider that extra probability because you already know you're going to not take the null hypothesis. It's already basically just random variation that we're seeing. So hopefully that makes sense. So the idea is we just want to be really extra careful about the probability number that we're using. And we want to make sure that we're not using one that's too small for our own good. And usually the convention with a sampling distribution like this is because of the symmetry. We check the same number of standard deviations away from the center. So we check both tails by taking the probability number we get and multiplying by 2. And we will do that in example 3 because the probability number we get is going to be kind of small, and we just want to double check those bases. Now, it really does come down to what we take as the alternative, though. Just so you guys are aware, if we were testing an alternative hypothesis like we were in the first example, where we wanted to check that the cracking rate was lowered, then we wouldn't have to check the symmetry condition. We wouldn't have to find the upper tail as well. But technically, because of this one where we're not using the word like decreased or increased, we do want to kind of double check our bases and check both of the tails, check all of the probability. Okay, was that enough time for you guys to kind of jot down any notes you needed to here? Cool. If you guys need me to, okay, it looks like we got a few thumbs up. So if you do need me to go back, I can always go back at the end of the class if you need to copy something up. But let's work on this last example today so we can get through this chapter. And those of you that do have proportions to work with for the data assignment, you can now kind of start thinking about how you want to set up your hypothesis test. So example number 3, we're going to look at a business by the looks of it. We are going to, I guess, survey 100 customers in a random way. And we find out that 73% of them are satisfied, maybe with like customer service or something like that. However, the boss has always claimed that at least 80% of his 1 million customers are satisfied. So should we accept his statement, or is he trying to get our goat? Not that I would ever do this if I worked for a business. I probably wouldn't go out of my way to survey 100 customers just to do a hypothesis test, but this is statistics, and we're going to put ourselves into weird situations anyway. I think it's beneficial maybe to have one last example showing both approaches, and we have enough time to do that. I think we have another like half hour. So are you guys okay to see another example using both approaches? You don't have to do this in practice, right? Usually what you're going to do is select one approach or the other. Okay, so yeah, I mean, let's do it because we do have the time, and that way you have lots of examples in your notes to fall back onto. So first things first, let's try to sort out the target and the sample. Okay, so we are going to be testing the hypothesis that our boss is correct or not. So the target population we're going to take to be 80%. Okay, so we're going to assume that the 100 million customers, that's the target population, and we're taking a sample of 100 customers from that target. And we are estimating that 73% of them are satisfied. 73 of those 100 customers are satisfied. So that's our target and sample stats. So what are we going to test? We would like to test whether or not our boss is true or whether or not he's shitting with us. So the target proportion is 80%. So we're going to assume that there's no change in the target proportion and that the data that we collect is really just the same as the target. Okay, so we're collecting some data and we're just going to assume that it's the same as the target unless we can collect enough evidence otherwise. I mean, if you wanted to use a less than symbol here, I wouldn't argue with you, but since there's nothing that says increased or decreased, and I would like to show you this two-tailed approach to thinking about probability, we're just going to assume that the alternative is that your boss is wrong. So either the boss is right or the boss is wrong. We're going to default to the boss is right because we don't have any evidence yet to assume that he's wrong. And of course, the alternative is that he's not wrong. He is a lying piece of shit. Okay, so that's what we're going to test. Let's check the conditions. All right, so first thing we want to check is independence. Do we have a random sample? I think it does say in the question that we did survey randomly, so at least we have some randomization. And then for independence, we also want to check that we have the less than 10% criterion satisfied. So we're going to take our sample size of 100 and verify that it's less than 10% of the target population, which is 1 million. Certainly that's true. So the less than 10% criterion is satisfied. Boom, so independence is done. Let's take a look at sample size. We have 73 successes in our sample. If we take somebody being satisfied as a success. And then we're going to have 100 minus 73 failures. What is that? 727? So looking at these two numbers, we see that the 10 and 10 criterion is satisfied. So the sample size criterion for our categorical data is indeed satisfied. So this means that we can use the central limit theorem. We know that our sampling distribution is going to have a mean of 0.8 and a standard error given by that square root. So that's all the setup. Now you would technically take one of the two paths, either forming a confidence interval to test or using the probability approach to test. Let's do the confidence interval part first. And it's not really given in the question here. So let's take a 95% confidence interval because it's not stated what kind of interval to take. So 95 seems like the appropriate thing to choose here. I'm doing a study on humans' happiness, I guess, but it's not like their life or death is at stake. If maybe human life or death was at stake, maybe I would take a 98% confidence interval, but I think 95% is fine. So we know our Z star cutoff value. I think that's 1.96 if I remember correctly, or 95. Yeah, so 1.96. So this means that our confidence interval must look like our estimate plus or minus our Z star cutoff number times what we call the standard error. And we're just going to fill in all of these numbers and kind of see where things fall. So we had a estimate of 73%. We have a cutoff number of 1.96. And we had 100. So here n is equal to 100 because we surveyed 100 people. And then let's pull up the calculator, do some calculations, and see where all this stuff lands. So 0.73. So we have a lower bound of 6.4. Let's go 6.43. And we have an upper of about 0.817. So let's just summarize our confidence interval and then make a conclusion based on our confidence interval. So about 95% of the time, we do expect our target population proportion to fall in between 64.3% to 81.7%. So So we're pretty confident that we're going to see a target population proportion somewhere in here. Now, I would argue that with this upper bound of 81.7, there might be a little bit of evidence to say that your boss could potentially be overshooting his satisfaction rate, but there's really not enough evidence, I think, to invalidate his claim completely. Because if we look at this interval, his number does technically fall on this interval. Right, it is falling pretty close to the edge up here. But I would say, we really haven't collected enough evidence to falsify his claim by any means. So there might be some small evidence to suggest to us that maybe he's overstepping his boundary a little bit. Maybe his satisfaction rate is actually maybe a little bit lower than what he thinks it is, maybe closer to 78% or something like that. But definitely not enough evidence to reject the hypothesis, the null hypothesis by any means. So we say something like, since P equals 80% falls on the interval, we don't have enough evidence to not, we don't have enough evidence essentially to reject the null hypothesis. Okay, so there's not enough evidence, in my opinion, to really falsify his claim. We're not going to reject the null hypothesis. So that's setting up, executing a confidence interval and using that to make some conclusion about the setup of our test. Let's finish up today's class by taking a look at the p-value approach, which is to see how far away our data that we collected. So how far away is 73% from the actual center of 80%? That's the p-value approach. Right, so in other words, how unusual is it for us to see 0.73 based on the data that we have? So let's maybe just calculate our standard deviation first. I'm just going to do that on my calculator back here. So 0.73 times 100. And let's take a few decimal places of accuracy. So 0, maybe 444. So let's take 4 decimal places just to get a bit of a more accurate number. And like I said, the more decimal places we take here, the more accurate our final percentages are going to be. And we want to have a decent accuracy because I noticed that these two things are pretty close to each other. So his assertion is pretty close to where the endpoint of this confidence interval is. So I do want to take at least some accuracy here just to make sure I get a better final percentage number. So once we have our standard deviation, then we're going to just draw ourselves a picture of the sampling distribution. So we know that for our sampling distribution, the center is our boss's claim, which is 80%. Now we went out and we sampled 100 individuals, and based on that sample, we got 73%. And so we're curious about what is the probability that we see a number like 73% or lower. So what are the chances that we see a measure of center based on our data that's 73% or lower? Okay, so this is the question we're asking. What's the chances that we see a number like this or lower? And then we try to figure out, based on the probability we have, if that's unusual. So we can do this using the normal CD. We have a lower number of maybe -100. We have our upper number given to us as 0.73. We've calculated the standard deviation of this distribution. It's rounded to 0.0444. And our boss has given us the measure of center, which is 80%. So let's put that all into the calculator and see what kind of probability number the calculator gives back to us. So mode distributions. We're going to do the normal CD. -100. And 0.8. Okay, and we get a probability number of about 0.0574. So let's take 0.0574. So this is arguably very close to what I would consider the boundary value of what I'm looking for. So because we're so close, I do want to look at the symmetry of this sampling distribution to make a final conclusion. So remember that we're kind of looking for a probability number of 5% or smaller. If we get less than 5%, as an overall probability number, then what we're seeing is kind of unusual. The point estimate we're seeing is kind of unusual. So ours is kind of on the borderline of being unusual at the moment. But what we're going to do is we're going to essentially take as much probability as possible. So we're not going to overstep our evidence gathering. And we're also going to look at getting a satisfaction rating on the other side of center as well. So if we go back to what our hypothesis actually looks like, we're just testing the hypothesis that it's different from 0.8. We do get the probability of seeing something 0.73 or less as around 5%, but we should also check the other side as well, because I could collect the data and I could get a number that's on the other side of 0.8 as well, being the same distance away from the center. So what we typically do is just take this probability number, we'll multiply it by 2, and that tells us the probability we see a measurement that's this far away or more from 80%. So let's write down that percent. 0.574 times 2, and that would be about 11.48%. This probability tells us the chances that we see as an extreme number as 0.73, but it could go in either direction. It could be less than 80%, or it could be in the other direction, which is greater than 80% too. So this is just kind of a way for us to not overstep our conclusion. And that's typically what we try to do in stats, is to not overstep. So we take this kind of larger probability number as a fail-safe measure to make sure we're not overstepping. And the key here is that we're checking in either direction. That's the key to why we multiply by 2. It gives us a picture that looks something like this. What is that? 7 away. So we'd also be testing to see whether or not we have something that's 87% or higher too. So it gives us this combined probability, and this combined probability is about close to 12 or 11.5%. So I would say that we don't really have enough evidence to suggest that our boss is lying to us. So we would not reject the null hypothesis once again, because we just don't have enough probability to do that. This is not really an unusual value to see. 73% is a value that I should expect to see, 1 in 10 times kind of thing. Oh, yeah, I kind of need to be careful here, right? There's lots of different P's, I guess. I just realized that right now, and this is potentially what some students found kind of confusing. If it's helpful, you can label maybe one of them as like a capital P or something like that, because the lowercase p is usually reserved for, yeah, sorry, I just realized this, and this was a big problem last semester. So the small lowercase p is typically reserved for the target population proportion. And when we're doing our confidence interval, we're not calculating any other kinds of probabilities. So all of these can stay as small p's. That's totally fine. But when we're using this kind of secondary approach, it is a little bit annoying with working with categorical data, because you're calculating another probability and the calculator spits out a little p. But that probability number we get isn't the same as what the target proportion population is. So if you need to, you can just go back and maybe make some of them capitals, or like I'll put like little underlines on my P's here, so you know which one represents the probability, which one represents the area, and which one represents, the little P's represent the measure of center of the sampling distribution. So sorry about that. I should have caught that a little bit sooner. So this 11.48% actually tells us the area inside of both of these tails. And because it's so large, it really is telling us that seeing something like 73% in our sample isn't unusual. So we are not going to reject the null hypothesis. There's not really enough evidence for us to suggest that our boss is lying to us, although it did come pretty close. Okay, so that's going to finish up the categorical data section. Hopefully you guys have a lovely rest of your morning. I'll stick around for a few minutes in case you have any questions or kind of clarification things you'd like to go over. But otherwise, have a lovely weekend. And don't forget to do the Section 3 test. That will be due by Sunday. So please put that into your calendars to do this weekend. And I will see all of you on Tuesday. Yeah, I'll be coming at you live from the college. You're very welcome, everyone. Very welcome. You're welcome. Have a good day.